Your heating system turned on this morning before you even opened your eyes. You never approved it. You never decided how long it would run. You never chose how much it would cost. A thermostat made that decision. A furnace answered the call. And somewhere inside a billing system you will never see, another number quietly increased. The average American household spends $400 every single year just heating a home. Stretch that across 20 years, and that becomes $28,000 handed over to a utility company that controls the prices, raises them whenever it wants, and sends a bill you're expected to pay without question because most people believe they have no alternative. But that belief is wrong. Right now, while you're sitting inside your house, the south wall of your home is being blasted with enough solar energy on a clear winter day to heat an entire room completely free. No wires, no solar panels, no permits, no monthly bill. And the device capable of capturing that heat and turning it into warm air, you can actually feel costs around $50 to build using materials that are probably already sitting in your recycling bin right now. Canadian homesteaders discovered this decades ago, back in the 1970s. Since then, people have been using this simple invention to heat garages, workshops, cabins, sheds, and entire rooms through winters cold enough to freeze pipes solid in only 3 hours. The shocking part is what this system is actually made from. Soda cans, a sheet of plywood, black spray paint, that is it. A homemade device built from trash has outperformed commercial $3,000 solar air heating systems in side-by-side tests. It needs no electrical connection, no inverter, no charge controller, no battery bank, no installer, no permit, no HOA approval because from the street, it looks just like another window. And the reason most people have never heard of it has nothing to do with whether it works. Stay here because what you're about to see will permanently change the way you look at the south side of your house. Your heating bill is not an unavoidable obligation. It is a choice most people never realized they had. Here is the number that changes everything. On a clear winter day, every square foot of south-facing vertical wall on your house receives approximately 200 to 300 BTUs of solar energy every hour. A BTU, or British thermal unit, is simply the amount of energy required to raise 1 pound of water by 1 degree Fahrenheit. Your furnace works in BTUs. Your gas bill is a BTU bill. A normal 10x12 FT room with an 8-foot ceiling requires roughly 4,000 to 6,000 BTUs per hour to stay warm during cold weather depending on insulation quality. A simple low-art 4x8 FT solar air collector mounted on a south wall can produce around 3,000 to 5,000 BTUs every hour on a sunny winter day. Think about that for a second. One $32 sheet of plywood and one afternoon of work can completely heat a room using nothing but sunlight for as long as the sun rises in the south. During daylight hours, your furnace is doing absolutely nothing the system cannot already do for free. The reason people continue paying massive heating bills while sunlight pounds against the side of their homes every single winter is not because the technology does not exist. It is because nobody profits from telling you that soda cans can replace part of your heating system. Furnace companies never had a financial incentive to put this invention next to thermostats in hardware stores, but the physics behind it are real, measurable, and incredibly powerful. Once you understand why this works, you will realize this is not some survivalist fantasy or internet myth. It is basic science that has been documented for over 100 years. Inside a soda can solar heater, 4 separate physics principles work together at the exact same time. The first is solar absorption. Sunlight carries energy across multiple wavelengths, including visible light, ultraviolet radiation, and near-infrared radiation. When sunlight strikes a surface, one of 3 things happens. The light reflects away, passes through this material, or gets absorbed and converted directly into heat. Black surfaces absorb approximately 95% to 97% of incoming solar radiation. Bare aluminum reflects nearly 85%, but black painted aluminum absorbs roughly 95%. The moment you spray those cans black, you transform them from reflective waste into near-perfect solar absorbers. Every photon entering the collector becomes heat instead of bouncing away. In direct winter sunlight, the surface temperature of those black aluminum cans can reach between 140 degrees Fahrenheit and 180 degrees Fahrenheit. Those are not guesses. Those temperatures have been repeatedly measured in university tests and real-world field experiments for decades. The second principle is the greenhouse effect. Sunlight passes through the transparent front glazing of the collector, whether it is glass or polycarbonate. That sunlight hits the black cans and converts into heat. But the heat re-radiates as long-wave infrared radiation, which glass cannot easily transmit back outward. So the heat becomes trapped inside. It is the same reason a car becomes dangerously hot sitting in the sun, even on a cool spring day. Sunlight enters easily, heat struggles to escape. Inside the collector, trapped air rapidly heats up as more and more energy builds inside the sealed box. The third principle is convection. Warm air rises naturally, cool air sinks naturally. As the air inside the collector heats up, It rises toward the top of the box. At the top is an opening connected directly into your room. Hot air silently pours inside without a fan, without electricity, and without moving parts. As that heated air exits, cooler room air gets pulled into the collector through a second opening near the floor. That creates a continuous convection loop. Cool room air enters through the bottom vent, travels upward through heated soda can columns, exits through the top vent at temperatures between 120 degrees Fahrenheit and 140 degrees Fahrenheit, circulates through the room, cools slightly, falls back toward the floor, and gets pulled into the collector again. The process repeats continuously from sunrise until sunset without making a sound. No motors, no power supply, nothing to break. The fourth principle is thermal conductivity. Aluminum transfers heat incredibly fast. It conducts heat around 8 times better than steel and over 1,000 times better than air. When sunlight heats the black exterior surface of an aluminum can, that heat immediately transfers into the air moving through the inside of the can. The aluminum does not waste time storing heat. It moves the energy instantly into flowing air where you actually need it. That is exactly why aluminum soda cans are not just a cheap substitute. They are practically the ideal material for this system. Plastic would melt, wood would char, steel would respond slower, but thin aluminum cans already shaped into cylinders create nearly perfect solar heating tubes using something people normally throw away every day. Now look at what a single collector actually delivers. A standard 4x8FT collector panel built with 32 aluminum cans inside a plywood box produces air temperatures between 120 degrees Fahrenheit and 160 degrees Fahrenheit, depending on outside conditions and sun angle. Passive airflow averages around 30 to 50 cubic feet per minute. Heat delivery ranges between approximately 3,000 and 5,500 BTUs per hour. During a clear winter day, the collector can operate for 6 to 8 hours continuously, generating between 18,000 and 44,000 BTUs daily. To understand how significant that is, remember that a normal residential furnace may produce 40,000 to 80,000 BTUs per hour, but usually cycles on only 15 to 20 minutes each hour. A solar collector running for 7 hours can equal multiple complete furnace cycles every single day completely free. In a properly insulated 120 to 200 square FT room, one panel can maintain comfortable temperatures throughout daylight hours without the furnace running at all. Add a second panel and capacity doubles. Add a third and suddenly a major section of an entire house is being heated by sunlight striking a wall that previously did absolutely nothing. The materials required are shockingly simple. Around 32 to 40 aluminum cans cost $0 if collected from recycling bins. One sheet of 3/4-inch plywood measuring 4x8FT costs approximately $28 to $35. Twin-wall polycarbonate glazing costs around $35 to $45. Or reclaimed window glass can cost nothing at all. A can of flat black high-heat spray paint costs around $6 to $8. Foam board insulation costs around $12 to $15. Add weather stripping, screws, silicone sealant, vent covers with backdraft dampers, and the total build lands somewhere between $50 and $80 depending on what materials are already available. If reclaimed materials are used, the total can drop as low as $15 to $20. The build process itself is straightforward, but every detail matters. Start by collecting and preparing the cans. For a standard Wolfram 4x8 panel, 32 standard 12-ounce aluminum cans are required. 36 cans provide extra room for mistakes or damaged pieces. Every can must be rinsed thoroughly and dried completely for at least 24 hours, because trapped moisture expands under heat and weakens the joints. Once dry, punch a hole approximately 3/4 of an inch wide into the bottom of each can while completely opening the top section, so air can flow freely between stacked cans. 8 cans are connected end to end, forming one vertical column, approximately 66 inches long. Seal every connection using high-temperature silicone or aluminum tape because even tiny leaks reduce efficiency dramatically. Build 4 complete columns and allow all silicone to cure fully before continuing. Then spray every column with 2 coats of flat black high-heat paint because the black surface is what converts sunlight into usable heat. Next comes the collector box. Build a shallow rectangular frame from 3/4-inch plywood measuring 48 inches by 96 inches with sidewalls roughly 4 inches deep. Paint the entire interior flat black because every dark surface increases heat absorption. Then line the inside with 2-inch foam board insulation to stop heat from escaping backward into the outdoor wall. Place the 4 painted can columns inside the box side by side, sealing any side gaps using foam weather stripping so air is forced directly through the can columns rather than around them. Cut a lower intake slot approximately 2 inches tall across the bottom width of the box and a matching exhaust slot at the top. Cover both openings with mesh screen to stop insects from nesting inside. The glazing is installed next. Twin wall polycarbonate is lightweight, durable, and transmits around 82% of solar radiation, while glass transmits around 90%, but is heavier and more fragile. Seal the transparent front panel tightly onto the frame using high-temperature silicone and secure it carefully while allowing slight room for expansion because polycarbonate expands noticeably under heat. Any air leakage around the glazing can reduce internal temperatures by 20 degrees Fahrenheit to 30 degrees Fahrenheit, so sealing the edges completely is critical. Mounting the collector correctly is equally important. The panel must face as close to true south as possible because even moderate directional errors reduce performance significantly. The collector should also tilt toward the winter sun at approximately your latitude, plus 15 degrees. At 40 degrees north latitude, the ideal tilt becomes roughly 55 degrees from horizontal. The lower vent should sit around 2 to 4 inches above floor level, so cool, dense air naturally enters the system. The upper vent usually exits around 66 to 72 inches above the floor. 2 wall penetrations connect the collector to the room. Backdraft dampers must be installed correctly because without them, the airflow reverses after sunset, allowing room heat to escape back outside through the cooled collector. When sunlight strikes the panel for around 30 minutes on a clear winter day, vent temperatures inside the room should typically measure between 110 degrees Fahrenheit and 145 degrees Fahrenheit. Hold a piece of tissue paper near the lower vent, and it should visibly flutter inward, proving the convection loop is running properly. If performance is poor, the most common causes are incorrectly installed dampers, leaking glazing edges, damaged can seals, poor tilt angle, or shading from trees and nearby structures. Even partial shading can dramatically reduce output because convection strength depends heavily on heat intensity across the collector surface. And this is the moment most people realize something uncomfortable. For decades, enormous amounts of free heat have been hitting the walls of homes every winter, while families continued paying utility companies thousands upon thousands of dollars. Not because there was no alternative, not because the science was impossible, but because nobody ever showed them that one of the most effective solar heaters ever designed could be built from the same aluminum cans sitting in a recycling bin outside their house right now.